Lesson 9 Nuclear Medicine Intro and Half Life. Here you have the understandings as well as the applications and skills. So, since we started IB, we have focused on energy changes during chemical reactions involving electrons. Nuclear chemistry looks at energy changes when the nucleus decays. So we're actually going to take a look at the nucleus. So the first thing we want to differentiate is stable versus unstable nuclei. The stability of an atom's nucleus depends on the number and type of nuclear particles present, the so-called nucleons, which vary in different isotopes of the same element. Stable nuclei have balanced forces among the nucleons and so are not radioactive. Unstable nuclei have unbalanced forces and an excess of internal energy, and so they spontaneously decay to form more stable nuclei in a process known as radioactivity. These unstable nuclei are known as radionuclides. So if you remember, in the nucleus, we have protons and neutrons. There is a nuclear force that holds them together. They're strong and weak forces. And if we have too many protons or neutrons where it's not an exact ratio, then we have an unstable nuclei, and energy will be released through a process of decay so that they can become more stable. So radioactivity involves the emission of energy and particles from the nucleus as an atom decays into a more stable form. The emissions are known as radiation. So as the unstable nucleus decays, some radiation will be emitted in the form of particles and energy, and then you'll have your stable nucleus left over. Now, as this occurs, it may occur in one step, or it may be a series of steps until you get to a more stable nucleus. Okay, so there are two types of radionuclides that you're going to come across. Those would be natural radionuclides, which occur in the environment. Some examples include uranium-235, potassium-40, carbon-14. All elements with an atomic number greater than 84, which is PO, polonium, and higher are naturally radioactive, which means they have no stable, naturally occurring isotope. We also have induced or artificial radionuclides. These are not found in nature and are made to be unstable through procedures that usually involve bombardment reactions with neutrons or helium nuclei at great speed. Many of the radionuclides we're going to be talking about in nuclear medicine are produced in this way. So let's just talk briefly about the subatomic world and the fundamental theory. We actually know that protons and neutrons are not actually fundamental particles, but instead are made of quarks. Quarks are arranged in sets of three, and changes in their type gives rise to some forms of radiation. This is the case where most particles have what's called antiparticles, which have equivalent mass but opposite charge. One example of an antiparticle is the positron, which is the antiparticle of an electron. Same mass, but it has a positive charge. When particles and antiparticles collide, mutual destruction occurs and energy is released as a form of radiation called gamma rays. So through this process of nuclear decay, one or more of the following events can occur: the ejection of a neutron, the ejection of a proton, the conversion of a neutron to a proton with the ejection of an electron, known as a beta particle, the conversion of a proton to a neutron with the ejection of a positron, and the release of additional energy by the emission of photons known as gamma rays. So, all of these can happen, some of them can happen, some can occur over different steps of the decay process. It just depends on the element that is decaying. Now we have something called transmutation. So after undergoing decay, some nuclei are actually now different elements. So transmutation is the process of transforming one element into another via radioactive decay. The daughter nuclei, which is the new element that is formed, is still unstable and they decay further. So let's talk a little bit about the processes that you need to know for radioactive decay. So the first one we have is alpha. So alpha radiation is the ejection of particles from the nucleus that carry a charge of 2 positive and have a mass of 4 atomic mass units. This can be denoted as 42He or 42 alpha, the Greek letter alpha. It represents or is equivalent to a helium nucleus. So you might see it in both cases. So here we have an example where a uranium-238 atom is unstable and it will decay into a new element, thorium, and it will lose this alpha particle. Now, the thing with nuclear equations that we're going to see is the mass that is on the left-hand side of the arrow must be equal to the mass on the right-hand side. So we can see that on the right-hand side, 4 plus 234 equals 238, and the atomic number must also be equal. So we have 92 on the left, and on the right we have 2 plus 90. The next type of radiation you need to know is beta radiation. So beta radiation is the ejection of electrons from the nucleus. They are formed during the conversion of neutrons to protons, so the mass number stays the same and the atomic number increases by 1. Beta particles are electrons, and so they have negligible mass and a negative charge. So you will see this as 0, -1 beta, or you might see 0, -1 E. So again, here's our example. So we could take a thorium atom. It can undergo nuclear decay and release a beta particle. We will see that the mass did not change. It is still 234, but the atomic number increased by 1, and thorium changed into Pa, which is protactinium. Here we have gamma radiation. Gamma radiation is the emission of energy as electromagnetic waves or photons. They have a very short wavelength, and they have high frequencies above 1000 hertz. They are denoted as the Greek letter Y, which is gamma. Gamma radiation results from energy changes in the nucleus and does not alter the atomic number or the mass. It often accompanies alpha or beta radiation, as the energy of the radionuclide is lower during radioactive decay. So why don't we try some examples where we have to write the nuclear equations for the following reactions, making reference to section 5 of the IB data booklet. So let's do the alpha decay of an isotope of radon that has a mass number of 219. So if we know the mass, we now need to know the atomic number. Okay, so you can go to your periodic table, find that the atomic number of radon is 86. That means you would start with an atom of radon, 219 on top, 86 on the bottom, and Rn for radon. Now, it says to do alpha decay. So check back to what alpha decay means, and you will see that it is 4,2 alpha or 4,2 He. Okay, so that is the particle, the radiation that is emitted. And as you will see in the answer, the atomic mass has gone down by 4. The atomic number has gone down by 2. So we have a brand new element, Po, polonium. So you can write the nuclear symbol for polonium 215, as you can see there. All right, letter B, let's do the beta decay of carbon 14. So if you look at your periodic table, you find the atomic number of carbon is 6. So we're going to do a beta decay. Hopefully you remember what beta decay looks like. That would be the 0, -1b. And when you add that as your product, because you are emitting or losing that particle, you will see that the carbon, the mass has changed, or has stayed the same. It is still 14, but the atomic number has increased by 1, so it is now changed into nitrogen 14. Radioactivity is known as ionizing radiation because it has enough energy to interact with an atom and cause the removal of electrons, and therefore the atom will become ionized. Radiation can cause the release of electrons other than those in the outer shell and form highly unstable radicals. Some radicals are so reactive that they exist for only a fraction of a second, immediately reacting with nearby molecules, causing chemical changes such as oxidation. So this ionizing radiation is highly energetic, and this causes a danger, right? This is why radiation is so dangerous. If it starts ionizing molecules in your body and causing really reactive radicals, you can damage cells and DNA. If the radiation damages gametes, you can even pass on hereditary mutations, and not in the X-Men good way. Since the most common molecule in the body is water, ionizing radiation can form a lot of OH radicals. Of the free radicals generated in these processes, the hydroxyl radical is probably the most dangerous. When it reacts with DNA, it can trigger a series of reactions which results in damage to it. Free radicals can also cause damage to proteins and lipids in cells. So hydroxide free radicals, those are the most potentially dangerous free radicals in the body. All forms of radioactive emission discussed here are ionizing, though they differ in what is known as their ionization density. This refers to the average energy released along a unit length of their track. Okay, so all radiation is ionizing, but some is more dangerous than others. Alpha particles with their +2 charge and relatively large mass have a high ionization density. X-rays and gamma rays, for example, have a lower ionization density, which means that at the same dose they produce radicals more sparsely within a cell. So here's a representation of 2 different examples of that ionization density. Each red dot represents an ionization, and the 2 examples represent the same dose with the same total number of ionizations. In letter A, you have low ionizing density radiation, such as gamma rays, more spread out. B, you have high ionizing density, such as alpha particles, which are more condensed. So now that we know about nuclear decay and radioactive materials, let's talk about half-life. So radioactive substances spontaneously decay at a rate that depends only on the nature of the substance. The reaction is not affected by changes in temperature, pressure, or the presence of other substances. In a first-order reaction for a reactant N, the rate expression is given there. Okay, so the rate is equal to the rate constant times the concentration of N. Okay, first-order reaction. This equation can be expressed in an integrated form, which is as follows. Okay, the thing you need to just take note in is the very last equation, which is given in the IB data booklet. Okay, so this is a way to look at the half-life, okay, which is the T 1/2, and you can see where it's equal to K, we have our rate constant. Okay, so don't worry too much about the first part, but pay attention to the bottom equation. So what all this shows is that the half-life of a specific radioactive decay process is constant. It depends only on the rate constant of the reaction, which is usually known as the decay constant in this context. So here we have an example of a reaction, a material that is decaying, and you could see what the graph looks like over a certain period of time. So let's talk about a practice question. An isotope of radium, which is given by 226 Ra, has a half-life of 1,620 years. Calculate the rate constant for the decay of radium-226. Okay, so we are given the half-life, 1,620 years, and it says to calculate the rate constant. So we're going to use that equation that was given on the previous page, K equals 0.693 over T 1/2. That is your half-life. So if you plug that in, you get K equals 0.693 divided by 1,620 years. And if you do the math, you get 4.28 times 10 to the negative fourth year to the negative 1 power. Note that the units of the rate constant of a first-order reaction are time to the negative 1 power. And the units of time in this solution must be consistent with those for the half-life. Okay, so since the half-life is given in years, our rate constant is going to be year to the negative 1 power. We have another equation that can also help us with half-life calculations. So there are two forms, as you can see there, that are given. They are the exact same equation. They're just manipulated a little bit. So again, this equation is given in the data booklet. And why don't we do a practice problem? What amount of iodine 128 will be left when 3.65 moles of this isotope is allowed to decay for 15 minutes? The half-life of iodine 128 is 25 minutes. Okay, so we know the amount of our isotope. We know how long it is allowed to decay for, and we are given the half-life. Okay, if we look at the previous slide, you can see the equation that we are going to use. All right, we can figure out the number of half-lives by comparing the amount of time that we're allowing it to decay divided by the actual half-life. Okay, so if we take 15 minutes divided by 25 minutes for one half-life, that means we've got 0.6 half-lives. Okay, we have not yet reached a full half-life, which means our final answer will not have gone down by 1/2 just yet. Okay, so that is where we compared t divided by t 1/2, the time divided by the half-life. Okay, let's see what is going on. So we are going to raise 0.5 to the 0.6 power. That's the number of half-lives. That means the proportion remaining is 0.6597. We take that proportion remaining and multiply it by our original amount, and we get that there are 2.41 moles remaining. All right, it says there, as a quick check, it is obvious that the time interval is less than a half-life, so it makes sense that the amount remaining is more than half the original amount. Okay, let's try this one. Number 22A. Formulate the nuclear equation for the decay of 90 yttrium, which is a beta emitter. All right, yttrium has an atomic number of 39 on the periodic table. Beta means you're going to have your 0, -1, B for beta. And when you put that in, you will see that yttrium has changed into zirconium because the atomic number has increased by 1. Letter B. The isotope has a half-life of 64 hours. Calculate how much of a 65.0 gram sample would remain after 4 days. Now this problem is just like the one on the previous slide. You're given the half-life, you're given the time that it has allowed to decay, and you're given the original amount. So you want to find how much time has actually occurred. Since we're given 4 days, we're going to convert it to hours because our half-life is hours. So 4 days is 96 hours. For a 1 half-life of 64 hours, we're going to do 96 divided by 64 to get 1.5 half-lives. To find the proportion remaining, we're going to take 0.5 and raise it to the power of 1.5. And then we're going to take that proportion remaining and we're going to multiply it by our starting amount. So we're going to take 65 times that 0.3536, giving us an amount remaining of 23 grams. So one thing to double check is that the math works out. So if 64 hours have passed, that means the amount would have gone down by half, which would have been 32.5 grams. Since this is more than 1 half-life, 1.5 half-lives, we've gone down some more, so our 23 gram answer makes sense. And last but not least, number 23. 228 actinium is radioactive. After 1 day, it is found that 0.33 milligrams of a 5.0 milligram sample remains. What is its half-life? Okay, so this problem is a little bit different than the ones before, but we can still figure it out. So we know how much we started with, 5 milligrams. We also know that after 1 day, only 0.33 milligrams remains. and we want to know what its half-life is. So we say it's after 1 day. So how much remained after 1 day? Well, we can do 0.33 divided by 5, and that gets us 0.066. Now the proportion remaining is equal to 0.5 to some power x, where x is the number of half-lives. So doing a little log of both sides gets us to ultimately get our x by itself, and we get 3.92, which equals the number of half-lives in 24 hours. Okay, so 3.92 half-lives in 24 hours. Well, one half-life is 24 divided by 3.92, which equals 6.12 hours, which is about 6 hours and 7 minutes.